Me?
Say it to the screen recording, Spencer.
No. Take it.
It's me?
There you go. Okay, here we go.
Are you ready?
Attention, please.
You gotta say it.
Please?
You gotta say it to the mic.
Like this?
Hold it lower.
Like this?
That is a transmitter.
Okay.
Put your hand down.
I'm confused.
Your hand.
Oh, like that.
There you go. Yeah. This has got to be able to see that.
I see. Ready?
Now hold your mouth.
Now I'll appear?
All right,
That was so difficult. Okay. What's the secret to the good relationship between the carbon atoms in benzene? Anyone have a guess? Okay. They let pi bonds be pi bonds.
This could be a learning moment. So, I need the microphone. That's actually pretty good.
Thank you. That was pretty good.
Yeah. All right. So guys, you should know enough about organic chemistry to know that we draw. You guys are going to stop doing jokes because I always make them serious and try to teach you stuff. But we may as well talk because you do need to know this. So you understand that in organic chemistry we represent molecules by lines with angles. And this is actually C6H6, which is benzene. On the corners there are carbons, and then on here there are hydrogens. So there's a hydrogen on each corner. So guys, what is the hybridization of each one of those carbons? Ooh, sp2. We have one domain, two domains, three domains. That makes this an sp2 hybrid. That means we have one unhybridized p orbital on each one of these carbon atoms. We see those unhybridized p orbitals forming double bonds around this ring. But what do we know about the location of those double bonds? They're simultaneously in all locations at once, which we call delocalized pi bonding. Thus, pi bonds be... What? Bygones be bygones.
You've never heard that?
The reason you've never heard it is because you've been raised in a culture that says if somebody makes you mad, hate them forever. So there's this thing called forgiveness that we're not very good at anymore. Right, yeah.
I've heard that one.
All right. Hey, so guys, there are 11,000 rumors floating around right now. I'm going to do my best to dispel as many of them as I can. I'm going to try to bring you up to speed in terms of what's going on right now. And then I'm also going to help you understand that everything that I'm about to say probably will change before lunch. So with that said, here's how this went down. 2 days ago, we crossed a threshold where we hit 30 cases, 30 active COVID cases within our school. That then put us in an environment where we then fell under the test to stay protocols. Guys, it's important for you to understand that these test to stay protocols are not being instituted by state or county health. This is not being instituted by the CDC. This is actually state legislation. Regardless of what you think about how our legislators at the end of last spring chose to manage epidemics. The legislators got together and they said, we want control. We don't want county health, state health. We don't even want the governor. being able to shut down schools, shut down businesses, implement mask mandates, all these other things. So they pulled all that power back and they brought it literally in-house. And as they were doing that, one of the things that they do is they passed legislation that said we're going to manage the opening and closing of schools. Understand that they did this in a period of time last April when we thought COVID was going to be in our rear view mirror, and 30 active cases in any particular school seemed like a stretch. Now those are days we miss. So right now we have more than 40 cases in the school. Anyway, all of that to say, that then placed us under state law. This is not Angela Dunn going, hey, we need to be careful here. This is state law. And the state law says that we as a school of less than 1,500 kids, when we hit 30 active cases, we have got to implement test to stay protocols. So originally we did not understand that this was law and not county health, state health. So an email went out yesterday to your parents and to your teachers. I don't know if you guys saw it too, that said, hey guys, we're now under test to stay, but if you've been vaccinated or if you've been a recent recovery from COVID, diagnosed COVID, you don't have to test. Understand that information was coming from state health officials. Then what happened is they started to think about this and they're like, wait a second, this isn't state health in the first place that's putting us under this test to stay protocol. This is law. And when they wrote the law was everybody gets tested. So they figured that out about an hour later and had to send out another email that said, no, forget what we just said. Everybody has to get tested because that's the way the law is written, based upon the 30 case. Anyway, you get what I'm saying. So the thought then became, hey, we've got to test everybody in the school in order to stay in school. And the state came to us and said, this was yesterday, the state came to us and they said, we're going to do this tomorrow. And the people in the district said, no, you're not. We're going to have to test 1,200 kids in a day, and you want us to do that tomorrow? We need some time to get this pulled together. So then it was, all right, we'll do it next Wednesday. So next Wednesday is scheduled to be a test to stay event. In the meantime, Alpine School District started to look at what they're doing up in Canyons District. Canyons District right now, they're having a blow up in cases as well. But guys, do you guys know about this? This is actually the end of second quarter in Canyons high schools. Their quarter went after Christmas. So up in Canyons School District, they wouldn't have school on Friday anyway, because unlike us that does minimal days, they give their teachers the whole day off to get grades done. So they don't have school on Friday. Monday is Martin Luther King Day. So what they're doing up in Canyons District is they're giving all of their students Thursday or Tuesday off, which then gives them Friday, Saturday, Sunday, Monday, Tuesday, 5 days. Happens to be the same length as the quarantine period, right? It's now 5 days. So what they were thinking up in Canyons District is if we can give our students an extra day off, that gives us 5 days, which counts as quarantining, which maybe then might mean that we don't have to do tests to stay. Alpine School District heard about that and said, that's an interesting option. Why don't we do that as well? For us, we were supposed to have school tomorrow, but that's why we have Friday and Tuesday as online learning days, because we're hoping that the precedent that they set in the Salt Lake schools will then carry over to us. We don't know yet if that's going to be the case. So this is where we are currently. Friday is an online learning day. Tuesday is an online learning day. We're still coming back to school on Wednesday, a B day, to a short day. They're always short, but it will also be a test to stay day, and they'll be calling us down to what we think the gym, they'll be calling us down to the A gym, kind of like they do for school pictures. Teachers please release A through C to get their pictures taken. Only you're going to be released to go down there to get COVID tested. It is not the deep PCR brain tickler test. It's the less invasive antigen test. If you're an athlete, it's the one that we had to do last year for Stay to Play. They just sort of swabbed both nostrils. 20 minutes later, you get your results. The way that this will work is everybody in the school gets tested. You'll go down there. You will need to have registered for the same system that we used for Stay to Play last year. And you'll get swabbed, and then they'll send you up into the bleachers, and you will sit there. And 20 minutes later, you'll get your results. If you're negative, you'll return to class. If you're positive, you will immediately start your 5-day quarantine. You'll just leave campus. I know, right? Then, guys, if you choose not to be tested, we have to assume that that is a positive test result, and you will be quarantining as well. So, but again, understand this has nothing to do with vaccination status or recent recovery from active infection. Everybody tests because that's the way the law is written. So that's what we know right now. There is the possibility that we will find out. Right now, Principal Jarrett is in a meeting learning more about this. There is the possibility that the state will allow our 5 days off to count as a quarantine period, resetting our COVID numbers, but we don't yet know. That means there is the possibility that we could return to school on Wednesday, and it will not be a test to stay day. It'll just be a day of school. But we don't yet know. So that's sort of the one thing that we're uncertain about. With that said, it is technically going to be an online learning day. But frankly, guys, recording again. So guys, what we are going to do for our online learning day is you're actually going to be doing a little bit of work on your own for lab. Let me just tell you. So guys, today in lab, we're going to be gathering our rate data. The thing that I didn't tell you is that, you know how I said we were going to use the data chart surprisingly in this lab? What I meant by that is we're going to gather the data in that data chart, and then remember I said that we were going to sort of fill out that space and figure out our rate law. What I meant is we're going to use that structure and format, but we're actually going to let a spreadsheet do the calculations for us. So your homework, if you will, during our online learning day will be simply to take your data from the lab we're doing today and populate a spreadsheet with it. I don't expect you to set up the equations that figure out how to figure out the rate law digitally. All that you're going to do is populate a spreadsheet with your time volume data, and then guys, we'll get back when I see you next, which could be sometime in April. I don't know. I'm not serious. But we'll talk about it later. So anyway, that's where we are. So guys, any questions about any this? Go ahead. I was just kidding. No, my point was just this is what we're talking about now. I would be really surprised if it's what we do on the next 5 days. What I'm saying is there's going to be a lot of changes. So we guys, if nothing else good has come of this whole pandemic, we're really good at being flexible, and we just need to continue to be flexible. So, yeah. The bottom line again, though, guys, is you will not have anything over the 5 days relative to this class. What you will be doing over the 5 days will be populating a spreadsheet simply with your data. No analysis, just populate a spreadsheet with your data in Google Docs. Don't do it in Excel or anything. Do it in Google Docs. Okay.
Told me that if you get tested and you get negative,
Yeah.
the guy like beside you or like in front of you get positive, you'll also be quarantined.
Yeah, that's not true. We and in no way slighting what your teacher told you, but we are no longer quarantining students based on contact tracing. So and you know that right now. I mean, there are people that are not. You know of people that have COVID right now. But you have, and some of you probably know that you've sat next to these people in other classes, and nobody's come to you and said, hey, you are out for 2 weeks. Can you guys believe we did that last year? Isn't that interesting? But the thing is we didn't even flinch. We were like, yeah, all right, I'm out for 2 weeks. Don't have it, have no symptoms, never tested positive. Because... Correct. And so but we're learning, right? And I mean, that's the thing that they say about pandemics is if you don't act immediately, you'll never have the chance to change your mind. And so they had no choice. We didn't know. But we're learning. So we are no longer quarantining based upon contact tracing. And guys, please hear this, unless it's someone in your home. If you have an active case of COVID in your home, then they will ask you to quarantine for 5 days and then test, assuming you're asymptomatic. But we're not contact tracing based upon school exposure. So yeah, no. Other things, somebody else, yeah. Yeah. So, and not only that, we need to talk. Has everyone taken the last test? I was frankly kind of waiting for Cole to get it done because you were sick before. Sorry, we didn't. I should have probably said that, but he's back. You're done. I just, you know what? We have so many people gone that I think everybody's done. Guys, to be honest with you right now, and I'm not making excuses, but I'm trying to explain. Since coming back from Christmas break, it's been amazingly crazy for me. Not only trying to manage all the ridiculousness of trying to figure out this COVID stuff, but just being honest with you, I forget how much work it is to have a student teacher. Some teachers are like, yeah, I love to have a student teacher because I don't have to do anything for 3 months. It's not like that. So I'm sorry if you guys are getting the short end of the stick relative to that, but that wasn't even your question. So, guys, I will get, well, I don't know. We may not, I can't even say that. I was about to say we may not even be in school in a week, but I think we will. But once the dust settles, I don't want you to do your next test until we get this test done. That said, if you're curious, sorry guys, if you're curious, let me show you the unit. So this is where we are right now, looking at temperature and catalyst. So then we get into chapter 15, equilibrium constants, equilibrium calculations, then Le Chatelier's principle, and then the test. So we have 4 more days of material, including today. At that point, I would grab the calendar and try to map that onto the calendar, but I have no idea what this is going to look like. So, but it won't be. Shoot, did I tell you guys I'm going to Mexico at the end of the month? Did I tell you that? Yeah, so So you guys don't even know this about me. And it's funny because I am not a beach person. Like if I picture where I would go on vacation, the last place I would go is to a resort to sit on a beach. But frankly, I married a woman who loves it, who has just poured that love into my children. And so, anyway, normally, I don't even know what that means anymore. Normally, once every couple of years, as a family, we try to just take a week in the winter and go somewhere warm. We haven't been able to do that for several years for obvious reasons. Like an idiot, I was thinking, hey, look, people are starting to travel again. You all are going to Europe and Hawaii and Antarctica. And hey, wait, my students are traveling. Maybe that means I can travel. And so, frankly, we have plane tickets and accommodations down in Cabo. this week, the week where January turns into February. You know, guys, maybe what that means, because you'll be with a sub, maybe what we could do, and I don't hold me to this, but maybe what we could do is we could maximize that time, and we could use that as a time for you guys to write up your previous test and then take the next test. Those are things that you guys could easily do in my absence. Look at me being a thinker, huh? See? So would that work? What did we, so mechanisms, concepts, no, shoot. Wait, where, oh, no. Wait, oh, sorry. K factors, no school, calculations, concepts, Le Chatelier's principle, whatever, we could make that work. I think that would be a good solution. I like that. Oh, that's true. But we'll make that work. Okay. You're going somewhere cold. I'm going somewhere warm. And frankly, I'd rather be going somewhere cold. But I think that's so cool. You're going to Antarctica. No. Yeah, she's going south, flying right over Cabo, and she's just going to keep going.
Yeah, what is the flight? So I actually fly to Atlanta and then Argentina and then Argentina and Argentina. Yeah.
Just the fact that you just said, oh, and I'm going to fly into Patagonia, makes me like 11 jealous.
Now we're getting like later, so that's actually what I'm most excited for.
So that's Cape Horn, right? Although, oh my gosh, that's so cool.
So yeah, I'm going to Antarctica.
Just to go to
with that.
Antarctica?
Kinda, I guess, yeah.
It's legendary.
I know, right?
And boats on kayaks.
Like your ski. Oh. That would be cool.
That is really cool. Yeah.
So my dad keeps saying he wants to sneak a sled in on bag and then sled on Antarctica. That's illegal, but
It's illegal?
yeah, you're not like allowed to do anything
Yeah.
to disturb the environment.
Yeah.
Like you have to sanitize everything.
They're really careful.
Went to Antarctica.
Oh, yeah.
Yeah.
We have amazing research bases down there. Hey, have you not seen Rudolph the Red-Nosed Reindeer? Yes, you can sled at the North Pole. Oh, Cade.
Or elk.
Or Elf, right. Okay, so guys, with all of that said, let's pretend like we have some time to do some chemistry. I know, it's a stretch. So guys, here... Oh, shoot.
No idea what they got me.
So, hold on. Guys, grab your homework. Wow. Oh, I'm still zoomed in. Okay. So let me grab a book. Oh, that's all me. Okay. So guys, let's take a look at these, and then were you all able to access the ones that I lifted out of the review book? You guys are okay? By the way, I actually ordered you your review books. They're now available. They'll be here Friday, which does us no good. But I'll get them to you. Again, they're my treat, because I can't charge you for them anymore. So anyway, no, it's really true, guys. I used to actually ask my students to pay for them because I let you keep them, because it makes sense to have you have the most recent copies. So I used to have my students, they're like $14, and I used to have my students pay for them. But then it got messy because, again, the legislature jumped in and changed the laws, and I can no longer ask my students to purchase things like that, and so I just pay for them out of my children's college fund. No, I'm just kidding. I have school money that I can spend. Guys, on these, allow me, if you would, to drive the process a little bit. We understand, as a brief introduction, this idea that elementary steps are simple steps that make up the mechanism. They can't be simplified. What you see is what you get. And we describe them by their molecularity, which is simply the number of things that are present as reactants in the elementary steps. Then, guys, we said that we can write rate laws for elementary steps from the balanced equations because they're elementary. There's nothing going on. There's no complicated things going on in the background. So, guys, we can simply write rate laws for the elementary steps from the balanced equations because the more reactant you've got, the faster the elementary steps go. So, guys, any questions on these? Okay, then we got to this point, and you'll remember that I told you that the book does not do a wonderful job of giving you examples of what you need to know in this material. And so, guys, on question number 77A, they were asking you to demonstrate that the elementary steps add up to the subject reaction. You'll notice that I represented it there. Understand that that's only half of the verification process. The other one is the rate laws matching for the overall reaction and the rate determining step. You'll notice, guys, in number 77, they actually told you, well, first of all, they ask you what is an intermediate. That's something that's created and then consumed in the elementary steps. And then, guys, they told you that the first step is the rate determining step. That is then the same as that's then the rate law for the overall reaction, because the rate law for the rate determining step is the rate law for the overall reaction. See how they came at that from a different direction? Then, guys, we skipped down here. One of the things that we did not talk about is that when you're verifying mechanisms, it's fair game if you need to double or triple or whatever elementary steps, if that allows them to add up. And so that was the case here. And then in 80B, what was that about? Their experimental rate is the same as the rate law. Okay, so that was similar to the previous question, right? They told us. Go ahead, Kate. It will tell you. Yeah. You won't. So, well, okay, so there's two ways that they could do this. They could tell you this is the rate determining step. Or they could give you a mechanism, and you can write the rate laws for the elementary steps, right? And then they could tell you the rate law for the overall reaction. And from that, you could identify the rate determining step because they would have to match. What they would have to tell you is they'd have to tell you this mechanism is good. Because remember what we talked about last time in class, the reasoning went like this. Here's a mechanism that might be good. And then they tell you the rate determining step. And the rate law for the rate determining step is the same as the rate law for the overall reaction. What they could also do is this. This mechanism is good. Here's the rate law for the reaction. Then you can write the rate laws for the elementary steps, and then you can figure out the rate determining step because they'll be the same. Does that make sense? So they could do that to you. And then, guys, again, they're asking you to talk about intermediates, and that's the end of this assignment, right? Okay. There are a couple things that I'd like to point out to you then that are actually contained in the thing from the book. Nope. So let me do this and this and this and this and this, and I thought, I know where I put them. Here, here, here. Okay. So guys, these are the ones from the book. Was there anything weird in this one? This one was pretty straightforward, right? Is that true? Was this one okay? Okay, so it's the other one then that I want to talk to you about. Here and Yeah, that's the one. Okay, so guys, I would like to talk with you about this one really quickly if we could. What can I do? Not that. Okay, hold on. Let me try this. No. Okay, I'm just going to zoom in. So, guys, this one got a little bit tricky. And the reason that this one got a little bit tricky, I'd like to talk you through, because this is something they could hold you accountable for on the AP test. And we didn't talk about it last time in class. So guys, help me if you would, please. On letter A, what's the rate law for the reaction? Rate is equal to K times what? Say it again. So it's second order in NO. And what order is it in bromine? First? Okay. So guys, is that okay? And you understand if you just wrote that down, you're nowhere near okay, because you needed to have those logical statements that say something like, referencing trials 1 and 2, where bromide concentration is held constant and the concentration of NO is doubled, the rate of the reaction, is that quadruples? I don't even know. It quadruples, therefore NO is second order. Yeah, that stuff. Okay. Then guys, letter B, that's just a little bit of math. Calculate the value for the rate constant. And again, you'll notice what it says, include units. You guys are focusing on that, right? The units are important. Then guys, number 2, it says, letter C, in experiment 2, what was the concentration of NO remaining when half of the original amount of Br2? Was that okay? Okay. Then guys, letter D, and this is where I wanted to pause. It says, which of the following reaction mechanisms is consistent with the rate law expressed in A? And then explain your choice. So guys, you'll notice here what they're doing is they're asking us to verify mechanisms, but they're giving us 2. So let's talk. In order to verify any mechanism, we need to write the rate law for the rate determining step, right? We don't even need to do the fast step. It doesn't matter. We need to write the rate law for the rate determining step. So guys, let's do the bottom one first. Here is our rate determining step. The rate law for that rate determining step is K times BR, and it's first order in BR. Guys, why first order in BR? BR2, why first order? Because that's a 1, right? The coefficients are the reaction orders. And this is not that, and therefore mechanism 2 double I, whatever, that one's no good, right? Is that okay? You're all right? But why is mechanism number 1 good? And guys, this is why. You've never seen this before. Equilibrium in a elementary step. So guys, picture in your mind's eye with me, if you would, what is equilibrium like? What's happening when something's at equilibrium? It's going both directions at the same speed, right? So I've never tried, never mind, I'm not even going to go there. Can we hold on for just a second? Can we relive the moment? Can you picture it going in? I seriously told friends about that later in the day. That was good. Oh yeah. That was good. All right, but guys, I was actually going to try to relate this to the balls thing, but I'm afraid it's not going to be a great relationship to the analogy, so I'm not going to go there. But let's just say this. We understand that when something's at equilibrium, it's doing and undoing itself simultaneously. So I'm trying to picture in my mind what that might look like, but I don't think it ties to the ball thing well. But could we simply say this? Because it's forming and unforming itself at the same rate, this and this become like synonymous. they become the same. So as we look at later steps in the element, in the mechanism, these things become equally available. Is that okay? But then, guys, when we think about that, here's what that means. We have, I can't erase right now, sorry guys, but we have an intermediate. The intermediate is the N2O2. So in order for this reaction, this might be a good way to describe it. So in order for this reaction to proceed, we need N2O2. But we always will have a source of N2O2 because this step is in equilibrium, which means that if we take away some N2O2 in order to mix it with Br2 to form product, guys, this is like Le Chatelier's principle that says as this goes down, it's just going to make more. So this first elementary step is like this little source of N2O2 that's always just making more as soon as we need it. Does that make sense? That's what the equilibrium thing does. And so, guys, fundamentally what that does for us in terms of our logic is this. So the idea is that this elementary step makes N2O2, but really what it's doing is it's also making NO. They're interchangeable. So that means we can take this and we can substitute. And now look where that gets us. Guys, that means that now the rate law for the rate determining step is K NO times NO, which is NO squared, and Br2, which is the same as the rate law for the which is the same as the rate law for the overall reaction if we allow our attention to simply go back to that. Is that okay? Yeah. And that's why it's substitutable. Uh-oh. Guys, forgive me. Just 1 second. Hello, this is Zach. Hey, how are you? Okay. No way. Okay. 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 Beautiful. Understood. Okay. 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 Awesome. Josh, thank you so much. And about the thing with the tires, I didn't have the opportunity to look into it. I'll follow up with you on that later today. All right, but let's not do that now. Okay, sounds good. Sounds great. Thank you. Bye. So my daughter hit a patch of ice, and her car went careening into the curb and just trashed it, and they're working on fixing it. So I knew if I didn't take that call, I'd never get a hold of them again. Anyway, so thank you. Sorry. So guys, are we good here? Are we okay, Santiago?
When I was looking at this, I was thinking to myself, in a reaction in equilibrium, there's like intermediate steps.
Yeah. Sorry, I didn't know the question was coming so quickly. Start again. Help me.
In a reaction,
Yes.
equilibrium,
Yes.
there's intermediate steps.
Oh, good question. And the answer is absolutely. So be careful that I'm answering your question, but I think what I heard you say was, in a reaction that's at equilibrium, are there elementary steps? Is that what you said? Oh, can there be intermediates? But if there are intermediates, that means there has to be elementary steps, right? Because an intermediate by definition is something that's created in one elementary step and consumed in a later elementary step. So let's pull this together. I love the way you think. So let's pull this together. So can a reaction at equilibrium have a mechanism? Can it have intermediates and elementary steps that make up its mechanism? And the answer is absolutely. Yeah, without a doubt. But this doesn't. We know that this step does not have elementary steps because we already know it's elementary. So this couldn't, but any other, so like for example this, N2 plus H2 forms NH3, which is ammonia, and it's not even balanced. That's not elementary. As a matter of fact, the chemistry is crazy complicated. As a matter of fact, the guy that figured out how to master this chemistry is rich beyond your belief. His name is Bjorn Haber. Anyway, so the idea here is that this is not elementary. There is a mechanism to this reaction, and Haber figured out how to maximize this mechanism, and some would say he actually helped us win World War II, because all of our, forgive me, but men were over in Europe and elsewhere fighting, and we didn't have many farmers around. And so the people that were farmers that were still around were trying to grow enough food for everybody. And in order to do that, they needed fertilizer. And NH3 is fertilizer. And the problem was it was really hard to manufacture because this reaction is really tricky. So Haber in the 1940s actually figured out how to maximize this reaction in a way that we had plentiful, cheap fertilizer, which then kept us fed, and you get the idea. So anyway, so the answer to your question is yes. So guys, are we good on the homework? Okay. So Kaylee, actually we talked on the phone on Tuesday. So guys, you let me down. I paused the screen recording in order to record your grades on Tuesday, and you didn't remind me to start recording again. So the screencast that I posted on Tuesday was 4 minutes long. I blame you. Just so what I did is I went, you passed the test. All right, guys. Actually, you know what? I'm realizing I probably should print my slides. The transitions today get a little bit funny at times. And by funny, I don't mean humorous like all of Spencer's wonderful jokes.
Wait, we never rated it.
Oh, gosh, right. So,
That's not on me.
shoot.
I don't get it.
Now, and guys, you have to remember that
I'm not doing comparative.
I always end up ruining the mood because after the funny, I make it serious. So you can't base it upon my response. So I'm here.
Yeah.
That was nice. Okay, hold on. Wait. Hold on. I suggest that we have 2, content and delivery. I'm going 2 thumbs up. Good content, well delivered. Yeah.
There's a struggle with the microphone.
That's a good point. Yeah.
That's the first time I used it.
Yeah.
Now it's recorded.
All right. Oh, yeah, I'm recording. All right. So, but I think we do need to remember that content, no, you're actually to blame for both. I was going to say that content he has no control over, but he is the one choosing the jokes. Delivery is all on him. So we got to be careful. Hey, so guys, here's what's going to happen. We spent a fair amount of time looking over homework. We spent even more time talking about our current realities. I know that I said earlier that in this class you weren't going to have something to do relative to the class. I'm just going to tell you right now, I don't think that's actually any longer true. We only have 30 minutes. I am going to ask, we're going to stop. I don't want to bleed into third period because I want you to collect your data in lab. By the way, you don't need to take your lab apparatus down. You can leave them set up. But guys, anyway, all of that to say, anything that we don't cover in the next 30 minutes, I am going to ask you to watch the screencast, and I'll just post the link to 2 years ago's screencast or whatever I can find. But guys, you're going to see that this material relates itself very well to the screencast. It'll be perfect. You'll be fine. But guys, I am going to ask that you finish today. Actually, you know what I can do? I'll actually grab one of the previous year screencasts and I will crop it down to the material that we don't get to, and then I'll splice them together. So what it means is you'll just... Does that make sense? I guess it does make sense, because for the people that are gone, it'll just be a clean view. And for you, you'll just have to scrub forward into the video to the point where today ends. That makes sense. Okay. So guys, let me explain to you where we're at by simply doing this. Rate is equal to K. If any one of you says M and N out loud, I'm going to turn around and hit you. Okay, go ahead. There you go. 2 thumbs down. Poor content, poorly delivered.
It was greatly delivered because you didn't even know you delivered it the first time.
It's because I didn't. No, it's not. There is not a rating scale for receiving the material. It's not funny because, actually it is funny because you think it's funny. Never mind. There should be our ability.
Therefore, delivery was really good.
It's a slippery slope. Okay. But guys, you do need to be able to agree on this. And this actually comes with a little bit of a warning about AP review. So guys, this is where we are right now. And it's so much more than just being able to write rate laws. Represented up here on the board is all sorts of interesting ideas that we need to talk about. So, what are A and B? They're reactants, right? So guys, when we write a rate law, the things that go in the brackets are the reactants, and more specifically, the reactants that have reaction orders that aren't zero. Can we dwell on that idea for a minute and agree? Guys, the things that go in the brackets are the reactants that have reaction orders that are not zero. But then this, guys, when a reaction starts, what is immediately and consistently happening to the values for these? They're going down. The very first day of class, we talked about the idea that reactions are always slowing down. And why are they always slowing down? Because the concentration of the reactants are always going down, and therefore the reaction is slowing down. Does that make sense? Okay. Now, guys, there is one thing here that I want to lay this in front of you for a moment, but then explain to you that we're not going to do this now. We'll do it during review. Guys, there is now one additional thing that the AP gods want you to understand about these rate laws. So here's what we know right now. We know that these are always going down, and as a result, the reaction is always slowing down. Are you okay on that idea? That's okay, right? But then, guys, this. You can actually graph this data. You can track rate versus concentration change over time. Did that make sense? You can track rate versus concentration change over time. Now, guys, let's talk. What's going to happen to the concentration over time? Come on, y'all. What's going to happen? It's always going down, right? So concentration is always going to be getting smaller. The rate, however, will not always change the same. Sometimes it will be linear. Sometimes it will be... Is that parabolic? What's the name for that from math, y'all? Logarithmic. And guys, here's the trick. by tracking changes in concentration and changes in rate, and by simply looking at the shapes of these curves, you can figure out the reaction orders of the reactants. Let me say that again. By tracking concentration change over time, always going down, right? Yes? Always going down. And by looking at how the rate changes over time, and by graphing that, guys, by simply looking at the shape of the curve, you can then figure out the reaction order. Now, guys, I'm going to tell you right now, I have skipped this every year since I started doing this, teaching AP Chemistry. I always skip this. It bought us a couple multiple choice points. It wasn't worth really spending time with. And to be honest with you guys, you just have to memorize the shapes of the curves. And you know me, I hate memorization. If you can't understand it, why teach it? You know what I'm talking about? But guys, I have no idea why, but in 2016, when they rewrote the curriculum for the test, this became a big deal. And you're going to see this. Even in free response, you're going to see this. So it's something I can no longer avoid. But I'm not going to teach it to you now because, guys, it's memorization. And to be honest with you, this book is the best place that I've ever found a summary of these relationships. So, guys, instead of teaching this in the flow of the unit, I'm not going to teach it to you now. We will go over it during the during AP review. The other reason that's more appropriate is we're not going to understand this, because to understand it takes calculus. We're not going to understand it. We're going to memorize it. And if you were to memorize it now, you'd forget it in May. If you memorize it in April, you'll probably remember. You know what I'm saying? Okay. So anyway, we're not going to worry about that right now. Okay, but guys, this is where we're then headed. Right now, we've talked about all these interesting rate concentration relationships, right? Because we understand there are 4 things that affect the speed of a reaction. One of them is concentration. What's the other 3? Temperature, surface area, catalyst. Guys, all of those, well, that's not true. 2 of the 3 of those change the value of K. Catalysts don't. How do catalysts change the rate of reaction? Drop the hump. We'll talk. But guys, that's what we're going to do today, is we are going to talk about the factors that influence the value for K. Temperature, surface area, and then catalysts. Although catalysts technically don't change the value of K, they drop the hump. We'll talk in a minute. You guys okay? Do you see where we're headed? All right. So guys, with that said, let's talk about, wait, we don't need to do that. We already just did all the review. So guys, let's talk about one thing that you may not have expected, but we need to do this in order to set the stage. Guys, the concept is orientation. Please write this down. So, guys, again, what we're going to do is we're going to step through the things that change the rate of a reaction: temperature, surface area. Orientation is not one of these things. But the reason that I'm introducing it to you now is you need to understand this when we get into catalysts. So guys, the idea is simply this. And I would encourage you to not, well, hold on. No. Let's write that second bullet down. So guys, the idea is this. You can have a collision that has enough energy to get over the hump. But the problem is this: if the collision is not aligned properly, they won't stick. So guys, I mean, this is a simple example, but it's actually pretty good. I don't even know if I can do this. But guys, imagine if I'm trying to bond an oxygen to a hydrogen, and in order to do that, I've got to stick them together like this, and I've got to add enough energy to get them to stick. You guys okay? Guys, we got to get these things to stick, but the trick is this. If they're oriented like this, it doesn't matter how hard they push, they'll never stick, right? A simple example, but I think that if you have that mental picture, guys, this is true of most reactions. In order for a collision, you don't need to write this down, but just see if this makes sense in your head. In order for collisions to be effective and therefore get over the hump, many times there's an alignment issue. For example, if you're trying to make this happen, if you're trying to get chlorine, atomic chlorine, to react with NaCl in order to form diatomic chlorine and then nitric oxide. Guys, in order for this to happen, obviously the chlorines have got to collide, because eventually this chlorine is going to bond to that chlorine, and that's going to turn into Cl2. Now, guys, the problem is if this collision happens and the chlorine does not run into the other chlorine, like it runs into the oxygen, they will still collide. And they could have enough energy to get over the activation energy hump. But guys, if they don't collide with proper alignment, the reaction will not take place. So this idea of orientation is important. Now guys, the more sensitive a reaction is to orientation, the slower the reaction will go. Does that make sense? That if a reaction has got a very tight margin for how they have to collide, that will be a slower reaction. Does that make sense kind of fundamentally? So guys, let me do this, because I know we're not going to get to it during our time together right now. This is what catalysts do. Catalysts, well, you'll see there's two kinds of catalysts. This is what heterogeneous catalysts do. A heterogeneous catalyst actually physically through intermolecular forces. Well, here, let's use this as our example. Guys, what a heterogeneous catalyst will do is they will grab a hold of this reactant and they will grab a hold of this reactant, and they will turn them so that their alignment is proper, so that they can then collide effectively. That's literally what heterogeneous catalysts do, is they grab a hold of reactants and turn them such that alignments are proper, increasing the likelihood that the reactions will be effective. Hopefully you're thinking to yourself, how the stink do they do that? And guys, the answer is you don't need to know this for this class. You need to know what they do, but you don't need to know how they do it. And if you would like to spend the rest of your life answering really interesting questions, become a catalytic chemist. Seriously, guys, the chemistry behind the way that catalysts work is absolutely fascinating. So, with that said, the catalyst that we're going to use in lab today, third period, that is not the way iodine catalyzes the decomposition of hydrogen peroxide. Sorry, I was stuttering there for a second because I was thinking. I know I stutter when I think. Guys, let's do this really quickly. Do you understand that heating up a reaction makes it go faster? Yes? And you understand that the reason why is because there's harder collisions more frequently? And do you also understand that adding a catalyst to a reaction causes the activation energy to go down? Is that okay? And do you also understand the idea that if we grind up a reactant, that it actually it causes more collisions, more surface area, and that causes the reaction the rate to go up because of more collisions, and that changes the value of K? Is that okay? Okay, what we're going to do, guys, is we are actually going to jump to the end of today. Everything that we just reviewed is the meat of the material that we're going to skip over. Guys, I'm going to skip straight away to catalysts. You guys understand that catalysts drop the hump, right? Okay, we're not going to dig into this a ton, but I am totally punting because I'm realizing that the best thing that we could do right now is skip into catalyst, because this is going to be beneficial for you during the lab. So guys, let's do this. Just follow along. Don't try to take notes. Just learn. So here's the idea. You understand that activation energy is a hump that separates reactants from products, right? And so the idea is that in order for a reaction to happen, the reactants have got to collide with enough energy to get over the hump, and then they turn into products. Is that good? So how do catalysts do this? How do catalysts lower the hump? And guys, again, you don't need to know the details, but what you should understand now is this. The way that a catalyst lowers the hump is by creating a new mechanism. Pause there. By creating a new mechanism. Now, guys, remind yourselves, what is a mechanism? The steps that a reaction goes through to turn reactants into products, right? The elementary steps. Well, guys, it turns out that literally what a catalyst does is it creates a brand new mechanism with brand new elementary steps, and those elementary steps have lower activation energies, and that allows the overall activation energy to drop and the reaction goes faster. So you need to understand that. How does a catalyst make a reaction go faster? It drops the activation energy. How does it do that? By creating a new mechanism that has a lower activation energy. Does that make sense? Okay, so guys, what does that look like? And the answer is this. It looks something like this. So, guys, for example, this is actually the chemistry that takes place in our upper atmosphere when we release chlorine into our atmosphere. I don't know if you understand this, but we had an ozone hole. Have you guys heard of that? Actually, what was happening is this. Ozone is O3. It's a molecule that actually creates a blanket that re-radiates solar energy back into space, and it keeps our Earth a little bit cooler. Well, what we discovered is that the ozone layer in the Earth was actually being depleted, and it was a crisis in the 1970s. What we finally learned is that normally in our atmosphere, O3, can you guys see that from a distance? Is that okay? O3, guys, just spontaneously breaks apart into O2. But this has a ridiculously high activation energy. So if you're up in our upper atmosphere, there's O3 up there and there's oxygen up there, and they will run into each other, but they got to hit really stinking hard in order to get over the hump. And so we have a lot of O3 in our upper atmosphere because it doesn't react with oxygen very well because the activation energy is high. Well, what we found out is this. This reaction is actually catalyzed by chlorine. And when chlorine gets involved in the dance, all of a sudden we have a new mechanism. This new mechanism actually has a different pathway, and it has much lower activation energy. Now, guys, the trick is this. With that lower activation energy, all of a sudden, these things are reacting together like crazy because they don't have to collide as hard in order to react. And all of a sudden, the rate of this reaction went through the roof, and a bunch of our O3 was being consumed and turned into O2, and that's where the ozone hole came from. But, guys, watch this. Check out the chlorine. Chlorine over here is a reactant, right? What about the chlorine over here? It's coming out as a product. And that's the thing that's scary about this. Chlorine is a reactant and chlorine is a product. And as this chlorine is produced after this reaction is over, it just comes back around and functions as a reactant. And guys, the chlorine never gets consumed. So the chlorine that we were releasing into our atmosphere actually was destroying thousands and thousands of ozone molecules because it was never being consumed. Does that make sense? So here's the question. Does that make chlorine an intermediate? Why not? What happens to intermediates? They are produced and then consumed. This is the opposite. This is consumed and then created. So guys, this is not an intermediate. This is a catalyst. So by definition, catalysts are substances that don't get consumed during the reaction. They can be consumed and then recreated, so they go in and come out unchanged. Yeah. So Chlorine doesn't get consumed by this reaction, but there are other reactions that consume chlorine in our upper atmosphere. So they did the math, and I think it was like 1,500 ozone molecules are destroyed by one chlorine atom on average, but then eventually those chlorine atoms will be consumed by other reactions, but it was like 1,500 to 1. It was unbelievable. So we couldn't get rid of the chlorine. It just had to naturally be consumed by other reactions. What we had to do is stop adding more chlorine to the environment and then allow those other processes to consume the stuff that was already there. So then the question is, where was the chlorine coming from? And the answer was hairspray and refrigerating units. So it used to be that the propellant in hairspray was, it's called they're chlorofluorocarbons. So it's literally, it's this. It's dichlorodifluoromethane. And this was actually the molecule that we were using. It's a gas. It's the molecule that we were using as a propellant for things like hairspray and stuff like that. And as we were venting this into the atmosphere, it's lighter than air. It floats up to the top, and the chlorine comes off and just starts destroying stuff. It's also the refrigerant in air conditioning systems in our car and in our homes. And it used to be that if you have somebody come to fix your air conditioner, the first thing they do is open a valve and vent all the refrigerant into the atmosphere. If you do that now, you'll go to prison. Not just a fine, it's a jailable offense to vent CFCs into the atmosphere. So if you work on air conditioning units, you actually carry a tank with you and you suck all the refrigerant out of the system, work on it, and then put it directly back. You can no longer vent this stuff to the atmosphere. And so by doing that, we finally allowed these other processes to catch up, and now it's not a problem. Anyway, although there is some evidence, we're starting to see another hole, but to my knowledge, I don't know why. So, you guys good on this idea about how these work? Okay, so guys, this then is where we need to go with this, and this is going to then lead us into the lab next time. Okay, so the idea then is this, and guys, you're going to want to write this down in your notes. There are, you know what? Hold on a second here, guys. Let me see what we can do here. Okay, so guys, do this with me, and then we'll be good, and we'll wrap up today. So guys, there are two types of catalysts. Sorry this is so scattered, but I know that we're okay. Guys, there are two types of catalysts. There are homogeneous catalysts, and there are heterogeneous catalysts. But guys, you remember that from general chemistry last year? Homo means the same the whole way through, and hetero means different. Do you remember that? So when we talk about this, guys, homogeneous catalysts are catalysts where the reactants and the catalyst exist in the same phase. This is what you're going to see in lab today. Hydrogen peroxide is a liquid. The iodide that you're going to use in lab is aqueous. That's the catalyst. So they're in the same phase. Those are homogeneous catalysts. There are also heterogeneous catalysts, and these are in different phases, and frankly, they're usually solids. So homogeneous catalysts, same phase. Typically, they go in as a reactant, they come out as a product, just like we saw with the ozone. Heterogeneous catalysts are catalysts that are in a different phase, and typically they are surfaces. They're solid surfaces upon which reactions take place. The great example of that are the catalytic converters that are in our cars. It's right before your muffler, and it's actually a canister that's full of a bunch of ceramic pellets that are coated in platinum. And as your exhaust gas travels across those pellets, the platinum acts as a catalyst, and it actually causes your exhaust gases to combust more thoroughly, so they're less polluting. And interestingly, guys, if you're at the position where you could figure this out, platinum, palladium, and nickel are all really good catalysts. And they all happen to be in the same group on the periodic table. They're also wildly expensive. You guys know about that, right? When some punks broke into the bus barn up at Canyon School District, this was like 4 years ago. They broke into the bus barn over Christmas break with a hacksaw, and they cut all the catalytic converters off all the buses, and then they turned around and sold them for the platinum for profit. You guys not know about this? Yeah, a catalytic converter has probably $40 or $50 worth of platinum in them. So probably for drug money, they stole the catalytic converters out of all these buses. So the bus drivers came back the first day in January and found their buses wouldn't run because the catalytic converters were gone. Yeah, that was not cool. Imagine stealing from a stinking school bus. Yeah, anyway. So guys, what I'd like to do to wrap up the day then is to show you this idea. So let's be clear. Homogeneous catalysts, they are in the same phase. They go in as reactants. They come out as products. That's what we're doing in lab today. Heterogeneous catalysts tend to be solids, and they are a surface upon which the reaction takes place. So guys, we may bleed into break just a little bit, but in order to justify bleeding into break a little bit, who is the only person that we would allow to make us miss a little bit of break? Kathy. Come on, Kathy. Teach us. I give you. I know. You know what? She's well. She sends her love. So, guys, would you do this for me? This sounds stupid. But would you watch this video with me? And the entire time, would you just keep in the back of your mind, you got to be stinking kidding me? Guys, this is a heterogeneous catalyst. Come on. Kathy. What's going on? Kathy.
A specially prepared metal surface of nickel or palladium contains active sites symbolized by the blue.
You guys, of course, are laughing at Kathy and not at me. Good.
A specially prepared metal surface of nickel or palladium contains active sites symbolized by the blue spheres at which a surface reaction can occur. When ethylene and hydrogen are exposed to this surface, they are adsorbed in a process called chemisorption. The H2 molecules dissociate into hydrogen atoms, bound to the surface but able to move about on it. When an adsorbed hydrogen atom encounters an adsorbed ethylene, it may add to one of the carbon atoms, forming a new CH bond. A second hydrogen atom then adds to the other carbon atom, forming ethane, which dissociates from the surface.
Guys, this is seriously like witchcraft. Okay, so let's watch this again. And don't take this for granted. Ready?
A specially prepared metal surface, nickel or palladium.
All right, so here we got nickel or palladium. Again, and platinum, those are great catalysts. But what does it mean to specially prepare it? I have no idea. What does specially preparing it do? Well, it makes some of these atoms blue. What does it mean that they're blue? And the answer is their polarities have changed. How do we do that? I have no idea. But what do we call these new blue different polarity points? We call them
Contains active sites.
Call them active sites. What makes them active? Well, guys, for some reason, their polarity has changed in such a way that they have the magic ability to attract the elements and molecules that are reactants in the reaction.
Symbolized by the blue spheres at which a surface reaction can occur. When ethylene and hydrogen are exposed to this surface, they are adsorbed in a process called chemisorption.
Why? I have no idea. But guys, they've done something magic that makes these active sites strangely attractive to these molecules, and you'll notice these molecules are symmetrical and therefore not polar in the first place. But somehow or another, these active sites grab a hold of things like hydrogen and this, which is methethane, and it grabs a hold of them.
The H2 molecule.
Not only does it grab a hold of them, it grabs a hold of them in such a way that the strength of the bond in the diatomic hydrogen is weakened to the point that it separates. So it separates the hydrogens into individual atoms, but somehow magically it can still hold on to the hydrogen atoms. But all the while it also grabs a hold of the ethane. But you'll notice that it doesn't hold on to the entire ethane molecule. What does it do?
Molecules dissociate into hydrogen atoms, bound to the surface but able to move about on it. When an adsorbed hydrogen atom encounters an adsorbed ethylene, it may add to one of the carbon.
What did it just change? What did it just change? The orientation. And now it's lined up in such a way that the hydrogen can now bond to the carbon.
Atoms, forming.
And now it grabs a hold of that. But look what happens. Now that it grabs a hold of that, the polarity of the carbon changes and it's no longer attracted to the active site.
New CH bond.
Off the surface of the catalyst.
A second hydrogen.
Oh my gosh, but isn't it convenient that this end is still attracted to that active site, and along comes the other hydrogen that another active site separated, and now
Atom then adds to the other carbon atom.
the reaction takes place, and now the polarity changes again, and this thing is now magically released. Guys, I'm fairly certain Keebler elves are behind this. Seriously, something here is happening. It's really, I'm saying this somewhat sarcastically, but the chemistry and the polarity and all the amazing interactions that this is describing, like this video kind of makes me sad because it takes something amazing and it makes it seem mundane. This is stinking crazy stuff. So, here's the wrap up, and then we will take a break. Is you don't need to know a lot about heterogeneous catalysts. You need to understand the idea of active sites. You do need to know that all catalysts drop the activation energy by providing a new mechanism. With that said, in lab today, we are going to use a homogeneous catalyst, specifically iodide ion that is found in potassium iodide solution. The potassium is a spectator. What we're going to do, guys, is we're going to allow that to decompose hydrogen peroxide. That is homogeneous, so the iodide, remember we drew it above the yields arrow, right? The iodide is a reactant and it's a product. That's why we put it up above the line. Yeah, it's both sides. And so it is a reactant, it is a product. It will show up in our rate law once we get to that point. Now, guys, the other thing I want to point out to you really quickly is this, and then we will take a break. There's one other thing that you need to understand, and I'm going to just ask you not to watch the screencast, but look this up in your book. The function of enzymes. Enzymes are biologic catalysts. There's some information you need to know in the book that you can look up, but guys, pay special attention to the lock and key model and take a look at that. And then, guys, at this point, here's your homework. So, guys, let's take a second, and here's what I'm going to suggest. Rather than me go back and post another screencast, guys, we really actually did a fairly good job based on previous understandings and what we just did with catalysts. We did a pretty good job of covering this material. So here's what I'm going to say. If you can answer the homework questions, you're good. If you can't, then guys, I will post a link to a previous year's complete day of material from today. But guys, only go and watch that if you can't answer the homework questions. Does that make sense? Okay, so let me stop recording, and then guys, why